money from my position. Lunchbox.
In this video, we're going to learn how to prove summations by induction. We are going to use the June 2012 question 2. The question reads, prove by mathematical induction that summation from r is equal to 1 up to n of r plus 3 as a factor of 2r plus 1 is equal to n over 6 as a factor of 4n squared plus 27n plus 41. 7 marks. Let's jump right into our solution. Well, as with an induction, we are going to start at the initial stage. At this stage, we want to prove that this statement here holds when n is equal to 1. So we are going to plug in 1 for n here, and for n here, and for n and here, to see if the result that we get on the left hand side is exactly the same as the result that we get on the right hand side. So we take the left hand side first. We plug in 1 for n here. So it becomes the summation from r is equal to 1 up to 1 of this expression here. So since it's the summation from r is equal to 1 up to 1, remember for summations, in order to get our terms here, we will be substituting 1 for r, then plus we substitute 2 for r, but in this case, we are not substituting 2 for r because our upper limit is what? Is 1. So we are only going to substitute 1 here. So the result of this summation shown here, if we substitute 1 here, we get 1 plus 3, which is 4. And here we get 2 times 1 plus 1, which is 3. So the result for this is 4 times 3, which is 12. Therefore, this is the result for our left-hand side. Then we move on to the right-hand side. We also want to check if we plug in 1 here, what do we get? So we get right-hand side is equal to 1 over 6, 4 times 1 squared plus 27 times 1 plus 41, which is 1 over 6 times 72 here, which gives us 12. And this 12 is exactly the same as the 12 that we got on the left-hand side. Therefore, the left-hand side is exactly equal to the right-hand side. Hence, this statement holds if n is equal to what? Is equal to 1. Hence, true for n is equal to 1. Then after that, we move on to the assumption stage. On the assumption stage, we don't prove here. We just state the result for such that if we check our original statement here, if we plug in k here, k here, k here, k here, we assume that this statement will be true if n is equal to k. So this is what we do. We come here on the assumption stage, then we plug in k here, 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 and here, and we leave it like that. Then we move on to the thesis stage. On the thesis stage, we also don't prove. We just state the result for n is equal to k plus 1, such that we get the summation from r is equal to 1 up to k plus 1 of r plus 3 as a factor of 2r plus 1, which is equal to k plus 1 over 6 as a factor of k plus 1 to the 2. We are just plugging k plus 1 here, here. So we have k plus 1 squared, then k plus 1 here. So we have written the result for n is equal to k plus 1, and we leave it like this. After the thesis stage, we move on to the proof stage. Here we're going to consider the left-hand side of the thesis stage. we take this left-hand side here. The left-hand side is equal to summation from r is equal to 1 up to k plus 1 of r plus 3 as a factor of 2r plus 1, which is this expression here. We want to play around with this so that we get something which is similar to the left-hand side of the assumption stage. Because as usual, on the proof stage, we take the left-hand side of the thesis stage, then play around with it a bit, such that we have an expression where we can substitute the right-hand side of the assumption stage. So in simple terms, on the proof stage, the left-hand side of the thesis stage marries the right-hand side of the assumption stage. So with summations, this is how we do it. You need to have basic knowledge of the sigma notation. Summation from r is equal to 1 up to k plus 1 of this expression here is the same as summation from r is equal to 1 up to k of the same expression here, plus the k plus 1th term. Why? Because on this summation, we're adding all terms from 1 up to the kth term. And we know that the kth term is the term just below k plus 1th term. So if we add all terms from r is equal to 1 up to k, then in order to get the summation from r is equal to 1 up to k plus 1, we just need to add the k plus 1th term, because we have already added the terms from r is equal to 1 up to k. Therefore, if you check this after doing this trick, if you check this, this is exactly equal to the left-hand side of the assumption stage here. Therefore, for this, by the inductive hypothesis, for this expression, we can substitute the right-hand side of the assumption stage. The assumption stage is also called the inductive hypothesis. This is why we have written by the inductive hypothesis here. In other words, we are saying by assumption, this expression gives us this expression. They are identical. Therefore, we have this expression plus the k plus 1th term. Now, the k plus 1th term is the answer that we get if we plug in k plus 1 for r here, such that we get k plus 1 plus 3, which is k plus 1 plus 3 here, multiplied by 2r plus 1, which is 2 times k plus 1 plus 1, 2 times k plus 1 plus 1 here. So after getting this, the remaining work is to simplify. We want to simplify this expression so that we get the right-hand side of the thesis stage. Remember, we have taken the left-hand side of the thesis stage. So we need to play around with this until we get the right-hand side of the thesis stage. If we can do that, then we would have proved that this statement is true for n is equal to k plus 1. So what we do here, we are guided by where we want to go. We have over 6 here on the right-hand side of this. This is where we want to go. So we need to find a way here. We need to find a way here to get 1 over 6 outside the brackets. Okay? So in order to do that, we simplify this bracket here, this bracket, and this bracket as well. What do we have here? K times 4k squared, we get 4k to the 3 plus 27k squared plus 41k. Then plus this expression here, we just remove the bracket here. So we get 1 plus 3, which gives us 4. So we have k plus 4, and here we have 2k plus 3. Then after that, we expand this bracket. We expand the brackets here, and we get this expression. This is exactly what we have. This is exactly what we have here. Okay, so I want you to follow closely what we did here. This 1 over 6 is only affecting the first bracket, but on our solution, 1 over 6 is affecting all the terms inside the bracket. So in order for us to have that effect here, we are going to take 1 over 6 as a factor, and we multiply this term and this term by 6. So if we take out 1 over 6 and we multiply this term by 6, what do we get? 6 times 1 over 6, they cancel out. 6 and 6 cancel out here. And we remain with 4k cubed plus 27k squared plus 41k. Since we have factored out 1 over 6, and we want to also include this term inside the brackets, we are also going to multiply every term here by what? This term by 6. So 6 times 2k squared, we get 12k squared. Then 6 times 11k, we get 66k. 6 times 12, we get 72. Then after we have this expression, we group some like terms and we simplify. After simplification, now we need to factorize the numerator. Why? Because where we want to go here, we have k plus 1 taken out as a factor, which means there was factorization here. And if you check correctly, this is factorization of a cubic polynomial, because if we expand the bracket by k, and here we have k squared inside here, we will get k to the 3, which means it's factorization of a cubic polynomial. So we come here and factorize this. We factorize the numerator only, because this is the numerator, 6 is the denominator here. So we let f of x is equal to this. Then we use trial and error method to find the first factor. So if we plug in -1 here, we get 0, which means that k plus 1 is a what? Is a factor. Then we proceed, since we have the first factor now, we proceed and use long division. This expression right here is the dividend, and k plus 1, our factor, is the divisor. Then if we divide this into this, we get this expression here. I'm assuming everyone is well versed with long division. Like for example, k into 4k cubed, we get 4k squared. Then 4k squared multiplied by k, what do we get? We get 4k to the 3. Then 4k squared multiplied by 1, we get 4k squared. Then we subtract this expression from this expression here. 4k cubed minus 4k cubed, we get 0. So there is no need to write 0 here. Then 39k squared minus 4k squared, we get 35k squared. As you know, like subtracts like subtracts like here. So we get 35k squared. Then there were no terms here. So we just drop this 107k. We drop it here, and we also drop 72. Then we repeat the same process. K into 35k squared. We get 35k. 35k times k, we get 35k squared. 35k times 1, we get 35k. If we subtract this expression from this expression right here, we get this. Then we repeat the same process. We get 72. We multiply here, we get this. And we subtract this expression from this expression, we get 0. Therefore, f of x is equal to the divisor times the quotient. Since there is no remainder, it's plus remainder, which is plus 0. So there is no need to write plus 0 here. So f of x is equal to this expression. Now, what do we have? We have our k plus 1 outside on the numerator, which is exactly what we want here. So we already have k plus 1 over 6 outside. Now we want to play around with this. We want to create a situation here such that we will get the right-hand side of the thesis stage right here. We want to get the expression inside this bracket. We want to play around with this expression so that we get here. So we have 41 here as a constant. So this is easy to do. We have 72. So we can split 72 here. And what do we get? We get 72, it's 41 plus 31. So we can split this, and we already have our 41 here. So now we want to create a situation with the remaining expression here, such that if we play around with this expression, we get this term right here. Because we already have 41, we already have k plus 1 over 6. So we want to play around with this. So we want to first obtain 27k plus 27 here. Why? Because we have 27 as a factor of k plus 1 here. So we are going to break this expression here. 35k plus 31, we are going to break it to remain with 27k plus 8k. This is still 35, right? Then on 31, we also want to remain with 27. So we are going to add 4 here so that our whole expression doesn't change, okay? So we get 27 plus 4. So now we have the situation that we want here. We can safely factorize now on the next stage. We can safely factorize this, and we get 27 as a factor of k plus 1, right? So the job that we have now is to play around with the first 3 to get what? To get 4 as a factor of k plus 1 or raised to the 2. That's what we want to do. So with these first 3 terms, we are going to factor out 4 here. After factoring out 4, we get k squared plus 2k plus 1. We're just dividing this every term here by 4. We get this. But from your mathematical knowledge, this is a perfect square, right? This is exactly a perfect square. Just because we just want to reverse from here to here, okay? K squared, in order to expand this, you say k squared, right? Plus 1 times k times 2, which is 2k, right? Then plus 1 squared, which is 1. So this right here, you must be able to recognize it as a mathematician that this is a perfect square. So you get 4k plus 1 to the 2. Then as a factor of k plus 1 here. So now this is the expression that we have on the numerator. Therefore, our left-hand side, remember we had dropped 1 over 6. We had dropped 1 over 6 here. We were just factorizing this. Therefore, our left-hand side as a whole was 1 over 6 times f of what? Times of f of x. And this is our f of x, right? Therefore, we have now k plus 1 over 6 here. K plus 1 over 6. As a factor of 4k plus 1 squared plus 27k plus 1 plus 41. Therefore, left-hand side is equal to right-hand side. Hence, true for n is equal to k plus 1 here. Since the statement is true for n is equal to 1, n is equal to k, and n is equal to k plus 1, therefore, by induction, it is true for all positive integral values of n. So that's it for today. Until next time.